As mentioned in our last video, we are skipping section 2 and going on to section 3, where we'll be looking at intersections, union, and compound inequalities. Now, these words may or may not be familiar to you, so let's give a little review. Now, in mathematics, which is what we're in, when they speak of intersections, a key word is the word and. And the symbol for intersections is an upside down U in a sense that looks like so. Now, when they speak of union, they're speaking particularly of the word or, and the symbol for union is this type of a U without that line right there. Okay, so two inequalities joined by the word and or the word or are called compound inequalities. Thus, when you have this inequality or this inequality, here they're speaking of a union, and this inequality and this inequality, they're speaking of an intersection. And this is just background to read it properly and to become acquainted with these keywords and the symbols. And of course, we'll be working this and developing what is in the textbook as we go along. Now, here are some other things that I won't read, but we will be reviewing each of these. Now, when we speak of intersection, again, the key word is and conjunction of sentences, here we see A and B, the intersection of A and B. In symbols, it would appear like this. Now, you may or may not recall from another course somewhere that they spoke of a Venn diagram in which I guess this was developed by Professor Venn, I'm assuming, that if you have set A, and there would be various members in this set, and you had set B, and there would be various members in this set, what you would be looking for if they're asking A intersection with B are those members that are found in both sets that, in a sense, intersect. So if we had, let's say, 1, 2, 3, 4, 5, 6, 7, 8, that in set A there was 1, 2, 3, 4, 5, and in set B there was 4, 5, 6, 7, 8, those elements that are found in both sets, that is, in the sense intersect, are 4, 5. Okay? And we'll be seeing an example of that shortly. Now, suppose instead of intersection, this was union, then what we do is just combine everything. It would be 1, 2, 3, 4, 5, 6, 7, 8 would be our union of these two sets. But as it appears there, it is just the intersection, members that are found in both sets. So let's go on and see what we have for an example here. Find the intersection of these two sets. So the methodology would say, let's see, I think I went, here we go. What's found in both? Well, we have a 1 here and a 1 there, a 2 there, and a 2 there, a 3 there, and a 3 there. So the elements that intersect, that is, are found in both sets, are 1, 2, and 3. And we give our answer in roster notation. Okay? Now for a little vocabulary, when two or more sentences are joined by the word and to make a compound sentence, the new sentence is called a conjunction of the sentences. The following is a conjunction of inequalities. So a negative 2 is less than x, and x is less than 1. Now, the word means that both sentences must be true if the conjunction is to be true. A number is a solution of a conjunction if it is a solution for both of the separate parts. For example, is negative 1 a solution? Or, for example, negative 1 is a solution because it is a solution of this sentence and this sentence. That is, negative 1 is both greater than negative 2 and less than negative 1. Now, we're going to look at a way to see this much more clearly as we go on. And here's the clearing up of this. So how do you do it? Well, basically, you are going to graph this first inequality, and that's saying that x is greater, reading it from the right, than a negative 2. So you put a that's a parenthesis, because it's only greater than, and then your solid line. Then you read the other one. X is less than positive 1. X is less than 1. So again, it's going to be a parenthesis at 1 and a line going to the left. Now, here's the part when the word is and you're dealing with an intersection. You're going to project these two lines together and see where they overlap. So it overlaps at a negative 2 going in this direction and a positive 1 going in this direction. So this is the graph now of the intersection, that is the conjunction of these two. Now in interval notation, again, looking at the graph carefully, you see that you're starting with a parenthesis at negative 2, comma, and going to a 1 parenthesis. That is your interval notation. And for set builder notation, bracket, x, is such that, now remember your x is in the middle here, and it's going to start at a -2, and it's going to be less than that this way, and then another less than sign, a 1. So again, we're using stuff from section 1 and building on our new vocabulary and symbols and coming up with a solution. And there is the set builder notation. And here they're referencing what we had said about the word and in math. It's a special word. Now we use the word and all the time as a conjunction, and this and this. Well, in math it has that special meaning of intersection. And you have to note if we're using it as that special meaning. And there's the symbol. So now they're asking us to solve and graph this compound inequality. Now, since it's in the middle, it happens to be an and. So we can think of it as this way and this part. Well, this part and then this part. Now, when we solve it, again, there is a strategy for it. And let me give you my interpretation of it. And the book is saying things very similar. So there it is. We want to isolate the x in the middle. So I'm going to subtract 5 from there. And to keep the whole thing balanced, I have to subtract 5 from all parts. So I'll put it over here. This adds up to a -6, less than or equal to now the 2x, because these cancel out. And this is going to be less than or equal to 8. Now, to get the x by itself, what I'm going to do is divide everything by 2. Well, I have to do it here as well, and here as well. So this then becomes a -3 is less than or equal to x is less than or equal to 4. Now while we're here, we can change it to set builder notation. We can write the interval notation of that because it's going to be, since this is equal to as well, a bracket, -3, and a bracket 4 for interval notation. And then to graph it, I'll just make a little graph here. -3, 4, and again we're using brackets and filling it in. So there's example 3 for you. It was a compound inequality, and it was an and we solved it, and we put it in set builder notation, interval notation, and we did the graph. And they're going to do all of this too for you here, I'm assuming. And it's all right here as well. So again, the book is a good place to look, and there's lots of reading, and that is what we're using as the basis of our course. Now, the abbreviated form of a conjunction like this can be written only if both inequality symbols point in the same direction, by the way. Okay? So solve and graph this and this. So another example. Well, here we can solve them individually and would use the rules we had in 4.1. Here x is greater than or equal to 1. Here it's x is greater than or equal to 3. Now, here's the key. Since this is an and, that is an intersection, when we graph the first one, and then the second one, and then project where they will intersect, it gives us our third one, which is our answer. This is the answer. These are the individual parts, but we're looking for intersection, and they intersect here. So the symbolization of this would be set builder notation, and union with set builder notation is this, the point of intersection. And then here, of course, interval notation is right there. Now, sometimes there is no way to solve both parts of a conjunction at once. So as you look at the Venn diagrams, we see there is no intersection between the two. So symbolically, writing A intersects with B, since there is none, there is no intersection, we say it's an empty set, or it's a null set. That is, there are no members. And there is no conjunction, so in a sense they are disjointed. They are said to be disjoint. They're not connected. Now, how would you show this in a graph? Well, once you solve it and you end up with something like this, and you see this is going this way, this is going this way, and when you look at areas of intersection, there are none. Now, again, all of this is true because we're dealing with the keyword and, which is intersection. Now, later, we're going to find where we do union, that's going to be different because we can join these, and I don't want to jump ahead too much, but just to let you know, that's the main difference. Because of the and here, we have a disjunction. They don't overlap. There is no intersection. So the answer is an empty or null set. Let's go on. All right, now we're going into unions of sets and disjunction of sentences. So the symbol changes from an upside down intersection to a regular sort of U, union. And once again, the key word will be or. So if this is 1, 2, 3, 4, 5, 6, 7, 8, now in union, it would include everything. So here we have set A being these, set B being these. Now if we were doing intersection, only the 3 is common to both. But since we're doing union, we now include all of them in our roster notation. Okay? Now, if you do have a disjunction, which they will show you, that's not a problem. Again, the key word is or for our union. So let's take a look at this. So let's take a look how specifically they're going to do it. Now, notice what's going on here. And by the way, we're building up for some stuff we're going to have a little later in future sections. So you need to really be careful about this. So we said x is less than -3, or this is union, x is greater than 3. So there's the first. There's the second. And now when we put them in union, we will have to join this part with this part. So how do we write this in interval notation? Now notice if you have the graph done, this is going to work out very well. Where is this coming from? Negative infinity. Where is it going up to? -3. Now, we want to show that this is union, so we actually use the symbol union, and then it starts at 3 and goes to positive infinity here. Now, there's no shortcut to this. Sometimes it could be even more complex than this, but right now this is a building stage. We're doing things simply. So in set builder notation, it would be this way with union, or you could write it this way too. Again, I would include these in your notes so they give you a model of what to do. All right, and let's see what we have for exercises here. And again, they're stressing the idea that the word or in mathematics has a special meaning, that is union, and that's the symbol. And then for a number to be used as solution of a disjunction, it must be at least one of the solution sets of the individual sentences. Not quite sure what they mean by that, but let's go on and maybe they'll show us something. Okay, let's look at example 8. Solve and graph this. So as you look at it, you see an inequality. You see another inequality. You see the word or, which indicates a union. So you're going to solve them individually. So you get this, or again, solve this. Notice that when they brought that 13 over, it became a -13, plus 3 became a -10. And then when you divided this by a -5, both sides, to keep this statement true, you had to reverse the sign. Okay? So you've got to this, and now you're going to graph this one. You're going to graph this one. you have a disjunction. When you put them on the same graph, that indicates your union. And it doesn't matter that they're interlapping or anything. And there is your graph of that. And then this is your interval notation. Again, right from the graph, negative infinity, -4 parenthesis, union symbol, bracket, 2, positive infinity. Now, again, I don't want the tape to get too long, but many times you may have to pause the tape to look at it and study it and be sure you understand it. And then, of course, if you have questions, you bring those into class. This is just meant to be a little review of the textbook. Now here they're giving us a caution here. Let's take a look at this. A compound inequality like x is less than -4 or x is greater or equal to 2 cannot be expressed this way, because to do so would be to say that x is simultaneously less than -4 and greater than or equal to 2. So no number is both less than -4 and greater than or equal to 2. But many are less than -4 or greater than equal to 2. All right, so again, read that over and keep that in mind. Example 9. Now here we have an inequality. It's an OR. So we have a union and this. So we solve each one. And again, since it's an OR, it will be a disjunction. And this is only x is greater than, even though it's on this side, we plot it there. And then here x is less than this, we plot it there. And writing it in interval notation is good. And then there is set builder notation. And again, this word OR is very significant. It indicates union. Now, proof of the pudding that you're mastering this will be your Quizme's. All right, let's do this one. Now again, in your textbook, they show all the answers. When you're doing an example, all you're going to have initially is the example. So let's pretend that we don't see any of this down below at this stage, and we just say this is what they want us to work with. So we see an inequality there. We see the word OR, which we know then will be a union, and another inequality. So what would the strategy be? Well, you're going to solve this, which is what they do, and they get that. And you're going to solve this, and you get that. And you note it's the word OR. Again, it's going to be a union. So you plot, in a sense, one graph. You plot the other graph. And this is where it's significant that as you join mentally these two lines together, instead of getting a disjunction, there is an overlap, and you get then a solid line. Ah, this is a little different. So what does this indicate? Well, interval notation, this is from negative infinity out on this end to positive infinity on this end. That is, in essence, all real numbers. Ah. Now this would be your set builder notation, but actually the union of this is all real numbers. So that's, again, I like the textbook. They did a really good job on this. Now, we're looking at interval notation and domains. Now, in some cases, as we look at this, that there is a little spot here where there's a hollow. What is the significance of that? Well, when we are defining our domain, we have to have values for our variable x such that if it's used in the denominator, it does not make our denominator a 0. If it does, then that value has to be excluded from the domain. And the strategy for it is to take your denominator, equal it to 0, solve, and say this is a value 7/3 that is excluded from the domain, because if x were this value, it would make your denominator a 0 undefined. So that's why this little tiny fraction right here on the number line, remember this is 2 1/3, 3 goes into there twice with 1/3, which is right there. So that in writing this, what would be the domain then of this function? You would say it comes from negative infinity up to 7/3, but it doesn't include it, so you have a parenthesis. Then you have the union symbol. Then you start on the other side of it at 7/3 and go up to positive infinity. Okay? Now, for number 11, here we have a function that is under the radical sign. And by definition, we can't have a number smaller under the radical sign than 0. Because as it starts to get negative, we get into the range of not a real number answer. So when we see things like this, what we do is we say this, which is the radicand, has to be greater or equal to 0. Because if it's less than a -2, such as a -3, you would say -3 plus 2 is the square root of -1, and that's not a real number. So you define this by equating the radicand, what is under the radical sign, as always being greater or equal to 0. So now you have what it is. So you're saying that x is greater or equal to -2. So that is your interval notation of the domain. And in set builder notation, again, all you have to do is put a little line, another x, and braces. And there's our three, our set builder, our graph, and our interval notation. Okay? And by the way, if you made a graph of this, it would look like that. Put that in your calculator. Again, we're not using calculators, but it's a good little tool. Now here they're giving us a few more things. Well, we're already at 36 minutes, and looking this over, it's a little bit tedious and perhaps beyond the beginning course we're in right now, but let's just do this one. Suppose we had the square root of 3 minus x. Well, what would our values be here? Well, again, the same technique. 3 minus x is greater than or equal to 0. So we just drop our x to the other side, and we get, let's put an x there instead of a 0. We're transposing the x, and that's our solution set. Now, if we write it this way, x is less than or equal to 3. Then, when we do our graph, there's our 3, and this is going to be a bracket facing to the left. Okay, now we get lots of negative values down here as we write it in, let me write this in set builder. This is defining the domain of this, and interval notation. And you might say, well, how come we have so many negative numbers if we're not allowed to have negative numbers under the radical sign? Well, because this x is negative, when you multiply a negative by a negative, it makes it a positive. But for instance, if we had positive numbers like 4, if I put a 4 in there, -4 and a +3, that makes that -1 again that you can't have. But x values can be negative. That's why this is what we have. Okay, we're not going to do that other little one. I think that's going to be a little too tedious, and we'll close this out.